I'm very pleased to introduce Kieran Kunhya from Open Broadcast Systems and John Mailhot from Imagine Communications. And they're going to be talking about something that's really important in the media industry today, which is ground to cloud integration. How do we get our signals from the ground into the cloud and back out? So we're going to start off with Kieran, and then he'll hand over to John. And this should be a really good presentation. Take it away, Kieran.
Thanks, Wes, and thanks for organizing again. So unfortunately, we have a very confusing term, GCCG, and I will try to explain it. Ground, cloud, cloud, ground. And I don't think anyone will disagree that if you have a better term, we are open to better terms here, because this is not the greatest term in the world. So over the last 2 years, we have lived our lives using the cloud. The substantial portions of our lives on Zoom, cloud-hosted email, social media, Amazon, Netflix, etc. Substantial parts of our life. However, television broadcast production has still mainly been on-premise. So pretty much all mid to high-end production still needs a switcher, usually an SDI, etc., etc. Even on web platforms, it's usually, if it's mid to high-end content, it's still produced in the same way as linear television. But in particular for sports, most of this equipment sits idle 23 hours of the day. It's used maybe 1 or 2 days a week. And it's very inefficient to want to pay for this equipment. So one of the benefits of Zoom, when everyone sat at home, Zoom could just scale up. When things opened up, Zoom could scale down in the cloud. And we don't want to start paying for resources that stay idle most of the time. Cloud production. But I've been doing cloud production. Yes and no, you kind of have, and you kind of haven't. A lot of these cloud production systems are single vendor monolithic applications, channel in the box, the lowest hanging fruit, playout servers, cloud switches. They do everything monolithically. Or you can do multi-vendor, but with some kind of proprietary transport, NDI being the most popular ones. Others actually do exist. But what we really want is an open standard for multi-vendor cloud production. Uncompressed exchange between the cloud instances. So I send to you, you send to me, but we know how to do it. And an agreed mechanism from going to or from ground and cloud. And one of the things we need to be able to do is get data back to the cloud and have it work into existing workflows. SDI, 2110, and for distribution, satellite, cable, over-the-air, terrestrial television. What's different is all of these have very well-defined linear timing models. SDI, ST2110-21, MPEG TS VBV, certainly SDI and TS VBVs have been around for 30 years, really well understood. 2110, newer, but still a very rigorous timing model. Why do we need a timing model? Well, if you don't have a timing model, you end up with variable or even undefined latency. Why is your web stream 20 or 30 seconds behind broadcast? One of the reasons, they don't have a timing model. Imagine you use web technologies for live production. You could cut between 2 camera angles and see a goal again. You could cut between 2 feeds and see a car overtake in Formula 1 because there is no strict timing model. And that's because they have variable delays. They have delays kind of based off time of flight and no real strict timing model. And this is one of the things we're missing in cloud production. So there's a few people out there that just say, I could do 2110 in the cloud. And I think there's some people claiming to do it. But there's quite a few issues to actually do it for real. At the moment, in any public cloud, that's not possible. There's no full PTP in the cloud. I think some clouds have some basic implementation of PTP now, but more for just synchronizing between instances. So if you have containers, you can do PTP with the host, but that's not the same thing as an actual PTP locked network. These cloud networks are shared. They're not yours. They have packet loss, sometimes substantial packet loss. And also, on a practical level, you don't really have access to advanced network card capabilities in the cloud, packet pacing, etc. for 2110. But also, 2110 is very linear. It's very lockstep. And actually, in a software world, we may not want to do that anymore. And actually, we don't. Cloud instances can process data faster than real time, sometimes marginally slower. But as long as, on average, we have a known worst case, and John will really go into the details for this, we can do non-real time processing. We have the other minor complication of synthetic sources, clips, graphics, etc., played out from the cloud. What timing do they use, and how do we reconcile that with the ground? Transport in the cloud is hard. The cloud is lossy, and if we want to do uncompressed video, we have to use some kind of protocol that underlies that, and they provide guarantees. So throughput with reliability, so all my data arrives correctly. But most importantly for broadcast, latency. All my data arrives within some kind of time-bounded window. a lot of these cloud transport protocols use efficiencies from other industries for big data, other things like that. That's fine if you're working on the wing of a Boeing 747. It doesn't matter if your data is, your model of that wing is a ton of data, but it arrives, I don't know, 100 milliseconds late or 500 milliseconds late. That's fine. But if that's a video frame, you've got a lot of issues. That said, it's quite different to existing open protocols in that you may not actually have visibility of what's going on underneath. It's probably one of the first times we're proposing a black box, but that black box is at least cloud vendor specific. You can move between cloud vendors and they have their own black box as long as they provide the guarantees I mentioned. Throughput with reliability, latency, etc. The Amazon scalable reliable diagram is datagram is such an example, and that's used in CDI, which I'll talk about because that's quite important. How does CDI compare to what I've talked about? Well, it handles many of the challenges discussed. It's an agreed way to exchange data between Amazon cloud instances of a particular type. They've defined the way pixel formats structures are done, metadata for things like HDR, audio formats, and they guarantee some level of throughput, reliability, and a bound of latency. They will guarantee that everything will arrive on time and the way you want it. You just don't know how it got there. And really, this is a big step forward for the industry. But there are some parts that do need input from GCCG, a more detailed timing model, and John will show you how really detailed we've got here. And GCCG itself could sit on top of an Amazon CDI protocol, really. So what is the Ground Ground Working Group? We're trying to solve this problem. Personally, I think the last difficult problem in broadcast production, we've done production over IP now. But really, how do I do a complex multi-channel production in the cloud with comparable latency to on-premise? So not 1 minute of latency like all these web platforms do. Something comparable. It won't be the same, obviously. We've disaggregated our processing delays. They're a little bit more, but they're not vastly more, shall we say. And get it to a viewer who's probably watching on a traditional chain, a traditional linear lockstep chain, and make all that work. Numerous technical challenges John will go through, and that's the link to the working group page. And then there's orchestration and control, the boring but important part, I'm afraid. How do cloud instances expose their capabilities, possibly based off the processing power they have, so maximum resolution, maximum frame rates, etc.? Is there some kind of orchestration layer that connects everything together? How do we handle changes in signal flow? We were just discussing with the NFL. An NFL broadcaster could be in 720p, it could be in 1080i, and it changes dynamically. You don't know what you're getting sometimes, and it can change on the fly. Connection status. Am I ready to receive data? How do I expose myself? And also, ground to cloud elements and vice versa. Those are relatively mature to an extent. This is a relatively known thing. There is ground to cloud going on today, but still not really orchestrated. It's just ad hoc. It's just fire some traffic to this port, pick it up on this port. There's no real orchestration. And I think John is next.
The first thing we did as a ground to cloud, cloud to ground working group is we tried to establish what are the operating points that people are operating at today for getting media to and from the cloud. And so, it's tempting to think about the big events, the most bestest thing you could do and say, okay, there's definitely a high end. And right now, the high end in the industry is to say we're going to use JPEG XS, and we'll use it at some, 3 bits per pixel or thereabouts. So it's a pretty nice picture. It's about the nicest picture you could want. And it works, right? You could do that, and it gets to the cloud, and you have a magically beautiful picture at the doorstep of the cloud in a very low latency. But it is a somewhat expensive operation to do it that way. There's a lot of other operating points people work at. So there's a striped J2K ULL, which is kind of the old school way of doing that. But if you're going to do the stripes, you might as well use JPEG XS because it operates at the same bit rate and has a much better computation footprint. There's full frame J2K, but the computation footprint of that is kind of ghastly. AVC Intra always seems like almost a good idea, but it doesn't ever get used for this. I don't know why. Well, and JPEG 2000 is a very different algorithm from JPEG XS. So the whole, JPEG 2000 really is a full frame codec versus JPEG XS is a incremental stripe codec, but with a rolling window. Well, it is 2023, yes. So 23 years. Not that it was done in 2000, but it was meant to be. There's a lot of use cases today that run at kind of an interactive latency around 20 megabit, H.264, VBV constrained. And this is a very common operating point. You know, NDI is sort of in that kind of zone, but it's not a long-op codec. It's Lord knows what it is. And there's paths and models for getting that there, right? And then there's kind of the Zoom quality or better, you know, the really low rate, trying to get a, you know, production out of a coffee shop. As a group, we had to pick, you know, what are we going to focus on? Which direction are we going to lean on? And each one of these has its challenges, right? So the bandwidth optimized H.264, you know, it exists. There's standards that describe it. The interactive latency kind of application here in the middle, again, very straightforward. There's standards that describe it. And then the highest rate ones are really these JPEG XS premium compressed. There's a whole set of standards there that we'll talk about that are new, but are the right things. Now, if the goal is to get to where, you know, if you build a facility on the ground today, you can buy a switcher from Grass and cameras from Sony and replay from EVS and, you know, router from Imagine and you know, something else from somebody else, and you hook it up and it works. And that's a beautiful thing. We would like to get to that same level of interoperability in the cloud. Now, that's where you have to say, well, what is that point of interoperability? What is the plane, the signal definition? Because you have to have a signal that's defined all the way through. So when you're going from the ground to the cloud, that signal definition is basically the thing in the IP network. So it's the IP packets and everything in the stack above that. So you know that the video is JPEG XS, the audio is 211030, the ANTS data might be 40, maybe there's a GRE tunnel or something to bind them together, and there's some kind of FEC or ARQ system to make sure you get it all there. Could be a -7 approach where you just send 2 copies, but you make these choices. At the end, there's a completely specified signal at this plane of interoperability. So if you were hooking up everything at the bottom like this, it's all well-defined all the way to the bottom. And that's more or less how 2110 facilities on the ground work. There's a specific set of choices through this tree. There's the packets look like this on the network, and the interoperability is there, and it works, well proven. But within the cloud, if I'm, you know, you run somebody's instance of one thing and somebody's instance of something else, what's the interchange between two things running in the cloud? That's where, to Kieran's point earlier, that's where the tricky part is, because you're not in a position to describe all the way down to the network what exactly is being sent between those instances. Because to get the performance in the environment of the cloud, you're relying on some cloud provider specific technologies. And so in one cloud it might be done one way, in another cloud it might be done another way. But there are comparable facilities available in different clouds. So the goal of the group is to say, okay, how do we define a plane somewhere in the middle that is that plane of interoperability? And so what this turns out to be is a definition of data buffers and data structures. So you have a bunch of pixels of frames, they're organized this way. You have some audio samples, they're organized this way. And then those buffers are the handoff point between this application sends it, this application receives it. Okay, that's good. You can at least define a plane of interoperability. It's just at a different level of the network than we usually are accustomed to. So you put stuff in the right format, you hit CDI send, CDI receive pops up, and the next guy says, here's your buffers. Well, that's all cool, right? And it works, except for that pesky timing thing that we talked about a moment ago. So within the VSF and within other organizations, there's a lot of work on standardizing all the parts involved in doing this ground-to-cloud stuff and cloud-to-cloud stuff. So first off was, how do we document that premium compressed use case? So the VSF has recently published TR08 and TR07 and TR09 underway. which describe very exactly how do you use JPEG XS to do this? How do you map it into 2110 timing model? How do you map it into really all the way down to the network packets is described by these documents. And that's great, right? Because it's a well-described, fully articulated system. And it's built on top of SMPTE 2110. It's built on top of the ITU JPEG XS codec. So literally every bit of the signal down to the wire is defined well. Now, the middle case we talked about, the H.264 transport stream kind of case, we sort of said, there's a lot of industrial knowledge of how to do that. The main thing that's not documented well in those cases is the control aspect. How do you tell a receiver what transport stream to take? And so that's on a punch list at AMWA to get worked on. I'm not sure it's the highest thing on the punch list, but it is in a queue. Then the biggest unknown really about especially the cloud-to-cloud part is this time flow and time tagging, the time model. That's where we're doing serious work in the VSF now on defining a timing model that can be applied, especially in those cloud-to-cloud transport cases where we don't want to replicate the frame-based lockstep, at the pulse of the frame, everybody moves one picture to the left. The cloud can do better than that, and we have to let it. And then, of course, there's a whole thing about the media containers and structures themselves for handing off between instances in the cloud. There are some well-defined models there. They could benefit with some improvement, so there is some work we could do there. So let's talk about the timing problem, because Kieran mentioned from the user perspective that timing problem is a big problem. The key is really that we want to allow variability. We don't want to be able we don't want to have a free-for-all, because that's how you get your signal to be 20 or 30 or 40 seconds late. So instead, you want to allow some variability, but be able to predict and bound the result of a chain of events. And so, you need a process, or if you're doing certain things in the cloud, like say you're trying to do an H.264 encode, you really need to take whatever your input is and harmonize it into a nice linear set of frames so that you can encode them and mark them correctly and do the VBV buffer and all the other things that you have to do as an encoder. So you don't deal well with input that arrives, all over the map. You have to be in a position to time bound how late could something be. So that's a requirement, right? Now, so I say, well, where does this variability come from? And we studied that a bit. There's some network contributions, but most of it is processing-induced contribution. The process steps themselves take a variable amount of time. And based on all that, we tried to develop a vocabulary about, just words that we use to describe, the transmission variability, and there's planning delay, how long is something going to take, and then talk about the variance on that. So I know this looks like math homework, and it kind of is, but we said right away, there are chunks of content, whether they're frames or stripes might depend on your application, but fundamentally you have a processing step, something comes in, it takes a certain amount of time to arrive, and there's some bounded window of variability on that. And then I do a thing to it, and I create output. Well, that output, if I think about the contract for the next guy, there's some minimum, how quickly could I ever act on it, which includes how quickly I can get the output out of my back end. And then there's some variability, what's my 99th percentile window of how likely I am to deliver. So maybe most of the time I deliver it right at the minimum, but sometimes it's a little later. I have to put a bound on, what is that 99th percentile, whether it's 99 or 99.9, you could argue, but basically a planning time. How long could it take? And then that way, if you have a processing step that's taking two inputs or is a concatenation of two things, you can model the accumulated latency. So these things might both happen in minimum time, but you can also model the confluence of those two probability estimations on the output and say, okay, what is the combined worst case thing? So this way, as you build a complicated system, once you have a vocabulary of these terms, you can model what is the latency through it and what is the minimum as well as the maximum. Because I'll tell you, handling the minimum case is also painful. Things could run fast. And as a device, the last thing you want to do is get suckered into, well, everything's running at minimum, so I'm going to set my time point there. And then suddenly a graphic or something comes through that took a little longer, and then everybody is suddenly you don't have the next frame you need. So modeling this timing so that as a device at the end of the chain, you've built in the right amount of buffering to handle everything running at minimum and what could have happened instead, up to everybody's commitment levels for worst case. That's the timing model. And that's the thing we're documenting now as a way that you can spec an application step has this well-defined timing model, so you can use it to engineer a system of those contributing elements. So you're giving each element in the software workflow variability to do its job in the best way possible, and permission to run fast, because sometimes you can take advantage of that. But at the same time, if you're a device at the end of the chain that has to recreate a linear sequence, you have the information you need to do it. So as a group, we've come up with a consensus path forward. And consensus building is hard. The organization has representation from telecom carriers, from broadcasters, from end users, from developers. Everybody has their own set of interest in getting the job done, but also their own view on what makes it hard. And that's what makes standards work really fun. And I mean that in a true, honest way. It's herding cats, but the cats all are hungry. The key to herding cats, in fact, is recognizing that they all like to eat. I'm not wrong about that, am I? You open a can of tuna fish and those cats will herd themselves. So there's an equivalent thing in the standards world, right? All of the participants want the work to get finished because they're trying to make products, build services, build studios, launch services. So we all have a vested interest as an industry in making these things work together. It's not quite as simple as the can of tuna fish and the cats, but it does work. And that's what drives progress. So for the case where you're handing off data between instances within a cloud, because that's the hard one, right? The first one, when you're going ground to cloud and cloud to ground, that work is pretty much done. VSF TR08 and TR09 give you a path to do that. It's well defined. It's defined all the way down to the bottom of the network. For the inter-instance case, where you're trying to coordinate between processes within a cloud, we have figured out and we've taken a few decisions. So we are going to use something like an extended version of NMOS, very similar to what's specified in Tier 09 actually, to identify things. So you can at least find the instances, find the endpoints. Obviously, we'll have to figure out a connection management schema. And again, ISO 5 may be a great template to build from. So there's some WIP and AMWA to look at using ISO 5 to represent CDI connections, for example. Within that, we need a way to describe content, but we can leverage the data definitions from 2110 to do that. We obviously aren't doing it exactly the 2110 way, but it provides a vocabulary to describe the meaning of the pixels, which is super important. The transport parameters, every cloud provider will have a different set of those, but they're knowable. And then the timing description, well, that's what we just talked about, is the work that we're doing now of describing the timing model of a given sender. Now, how to actually format the data that's at that interoperability plane, again, there's an existing definition in GitHub that's part of CDI that might be usable more generally. There's other ways to do it that seem appealing and might have a lower computation footprint, but they're not as well written down, let's say. So that's a discussion that's happening, but I think the base interop format that's defined in GitHub probably will be the one that carries for the near term because people have started doing some work in it. It's kind of like why racks are 19 inches wide. It has nothing to do with equipment design. It has to do with relays that were made in 1940. But once people started building racks, that size has stuck with us to this day. Yeah, it was a Western Electric relay rack, except a different version of it, because those were 24. So that's really the big work that's left to do. And then for the, if you're handing off within a cloud, but between people who aren't coordinated in any way, that almost just looks like a ground to cloud thing again, because you're not coordinating the instances. So this middle model is about things that are coordinated within a placement group. They have the right security envelope that they can hand things to each other and so forth. So all that said, that's the work going on in the VSF. The VSF is open for new members. It's a great organization, and that's where this work's happening. So what's next? Well, we have some WIP to document, and AMWA is working on some parts of this. We've already published TR08. TR09 will be published any day now.
So we do have time for one or two questions, if anybody has anything.
You talked about measuring or working out what the 99%, you kind of alluded to the fact it could be 99.9%, but surely at some point we care about every frame, so we want 100%. Are we going to have to allow for the fact that some frames will not get through at some point and we just have to live with it?
It's a statistical distribution that's, what's the word, discrete. So at some point the tail goes to nothing. So whether it's 99 or 99.99 or whether it's 99. He could have called it T99.9999, but this is jargon enough as it is, this topic. So yeah, we'll have to pick a number and decide what that number is, probably based off some experimental, or it's advertised. It will be some in the control plane.
Yeah, but I think really it's a contract, right? So if the frame's not there by then the receive side's going to take some action, use the previous frame, whatever. But if you're trying to reassemble the sequence of time events, yes, a frame could get dropped. And when it comes back to the ground, the frame synchronizer could drop it anyway. There's always that chance. But to build practical systems, we have to put some bounds on these things. And in error correction coding, the same thing happened, right? So DVB came up with a nice term. They called it quasi-error free, which means that over any reasonable observation window, that problem doesn't happen. But you can't prove that it would never happen because, you get into 10 to the minus 10th, 10 to the minus 11th, 10 to the minus 12th error rates. You can know that it will happen one day, but you won't want to stand there long enough to prove that it did or didn't.
Just a further comment. The transaction timing is also important, as we've been discussing. So it's not just the processing time, but there is a finite, and it can be relatively significant finite transaction time, and there is, as has been alluded to in CDI, some bounding on that. So you actually you have a similar transaction on that.
Oh no, just that the model needs to include both the bounds on the thing you did and the bounds on the getting your output out of you.
Thanks again to John Mailhot from Imagine Communications and Kieran Kunhya from Open Broadcast Systems. Thank you very much.